Hi, this time we're going to learn how to identify regions of areas under the normal curve. In the previous lesson, we've been acquainted with what the normal curve is, and we've also been introduced to the z-values or z-scores. To start this discussion, we're going to recall some of the previous concepts that we can utilize now, including this equation which shapes the normal distribution according to the mean and according to the standard deviation. To fully grasp what those two variables do, we create two graphs representing the change in the mean and the other representing the change in standard deviation. We let the mean approach 0 and the standard deviation approach 1. By doing so, we create a graph for a special case of a normal distribution, characterized by having a mean equal to 0 and a standard deviation equal to 1. This is called the standard normal distribution. This is the distribution that we're going to utilize to characterize the probability distribution of a continuous random variable. Now, continuous random variable in this case could be a measurement of a random person's height. Now, as we all know from the previous lessons, continuous random variables had outcomes that are unique to each other. In fact, they're all unique that it is easily said that continuous random variables have an infinite sample space. Now suppose we want to find out the probability of a continuous random variable is exactly equal to something. So what we do is divide the frequency of that something over the possible outcomes. Now, since all values of a continuous random variable is unique, the frequency count of something is just equal to 1 and we divide it with the elements of an infinite sample space. 1 over infinity is equal to 0. To visualize this, we graph the probability versus the number of outcomes. By just increasing the number of outcomes to approach it to 100, we can see a very fast drop in the probability. In fact, if we continue this increase in the number of outcomes to infinity, the probability approaches 0. To further justify that claim, we are going to set up a graph of the normal distribution with their corresponding axes. But first, before going to this, we first need to acknowledge a certain property, that the continuous random variables and their probabilities are represented by the area under the normal curve. So suppose you want to find out the probability of z exactly equal to 1. That is represented by the orange line. But since a line has no width, therefore it has no area. Thus, the probability of z exactly equal to 1 is 0, which is the same as saying that the probability of z greater than equal to 0 is the same as saying as p is greater than or z is greater than 0. Suppose we want to find out z is greater than 1, probability of z greater than 1. That is represented by the shaded area. So we knew that this time the probability is greater than 0. In fact, that is the integral of the equation that we've given earlier, which is a rather complex process. So statisticians have introduced the z-table, which utilizes the z-scores or z-values to find the corresponding areas under the normal curve. What we're going to do is to list all the elements of the z-table on the right and graph the normal distribution on the left, or the standard normal distribution. Suppose you want to find out the probability that z is greater than or equal to 1.25. That is represented by the yellow shaded tail on the right. So how do we go about this? First, we need to decompose 1.25 into 1.2 and 0.05 and find their values on the vertical and horizontal axis of the z-table. We take note of their columns and rows and intersect them together. By doing so, we arrive at a number 0.3944. But is this the number that we're looking for? The answer is no. This is the probability that z is in between 0 and 1.25, which is represented by the red shade below. So to solve this, we need to remember that the sum of probabilities of all outcomes is always equal to 1. And this is the same for the normal curve. And also, we need to remember that the normal curve is symmetric about the y-axis, such that the area on the right and area on the left is equal to each other, which is half of the total, which is 1, so 0.5. To solve this, we need to subtract the probability we got earlier, which is in red, to half of the total area and then the normal curve, which is 0.5. And by proceeding with the subtraction, we arrive at an answer of 0.1056, which is the area of the right tail that we're looking for. If you've noticed, the z-table only gives values for z in between 0 and a positive constant. And by symmetry, this is the same as z in between negative constant and 0. So we can use this to our advantage in the future problems that we're going to solve. For example, what if we want to find out the probability that z is in between 0 and 1.07? This is the same to the format above. So we decompose 1.07 and look for them in the vertical and horizontal axis. And we intersect and arrive at 3577 times 10 to the power of negative 1, or 0.3577. Now, is this the same on the left? Well, yes, of course. This is because of symmetry. Now moving on to a fairly more complex example, we want to find the probability of z being less than negative 1.01 and greater than 0.55. What we do is decompose that probability into two corresponding tails on the left and on the right. So this is the probability that z is less than negative 1.01 and z greater than 0.55 in blue. We list all the calculations for the red tail on the left and the blue tail on the right. Again, we utilize the properties that we learned earlier. So as you can see, we're subtracting from half of the total area under the normal curve. And we have this value, for example, on the left, we have this half of the normal curve minus z is in between negative 1.01 and 0, which is equivalent to z in between 0 and 1.01. So whatever that area, we reflect it on the left, which is the same because of symmetry. Then we subtract and arrive at the area that we're interested in. What we're going to do with the left side is the same as what we're going to do with the right side tail. So again, we have half of the total area minus the probability that z is less than 0.55 but not less than 0. So we subtract those areas, and as we proceed with the calculations, we're going to find out that that area is the area that we've been looking for. So by doing this, we can easily arrive at the desired area that we need, which is the areas in the tails. So starting with the red area, we have 1.0 and 0.01, intersecting them arrives at 0.2438, and subtracting from 0.5, we will get the final answer of 0.1562. Now doing the same thing for the the blue tail, 0.5 and 0.05 intersect and we arrive at 0.2088, and subtracting it from 0.5 will give us the final answer, which is in this case equal to 0.2912. Now, adding those two probabilities together would give us the final result, which is equal to 0.3650. Now, one concern with this is that the z-table only provides two decimal places for the z-scores. So for that, we introduce interpolation. This isn't part of the module, but I want you to learn this for future applications. So suppose we have z-scores from 1.43 to 1.44, which both can be located in the z table. And below are their corresponding values on the z table. But suppose, what if we want to find out a value that lies in between them, which we cannot find in the z table? For example, 1.435, which has 3 decimal places. So what is the corresponding value on the z table for that? To do that, we have to take note or keep in mind the lengths of those segments, and from that we create ratios. So we label them or their lengths to A, B, C, and D, where each of those lengths are subtractions of their endpoints, and X is the unknown probability located in the blue segment before. I want you to pause this video if this calculation seems very fast, but to save time, we arrive by solving the equation to a value of X, which is 0.42435, which is equal to the probability that we're looking for. So this is just the same as averaging between the two values, but this is also applicable to values that does not lie in between or exactly in between the two adjacent z-scores in the z-table. So proceeding with the discussion, if you have a Casio 991ES or a Casio FX570ES or the plus versions, you can easily find the areas under the normal curve under the stat function or stat mode. By just following the instruction of key presses on the top right or top left corner, we arrived at a very useful tool, which is the stat mode and the distribution tools. So first, we're going to press shift 1, 5, then 1 again to access the P function. Now what does the P function do? So let's try P of 0. So equals, that is 0.5. Now that is the shaded area on the graph right now. That is the left tail of the normal distribution, ranging from negative infinity to 0, or just z is less than 0. So let's try 1.25 this time. Now that is equal to a bigger number. This is represented by the shaded area region now. That is the left tail where z is less than 1.25. Now we're going to access Q by again following the key press instruction written up above, and Q0 is just equal to 0 because that is the probability of z exactly equal to 0. But let's try Q1.25. Now this time, that is the probability where z is in between 0 and 1.25. This is exactly equal to the values that we get from the z table. Moving on, let's try the function r, which I think intuitively written or to represent a right tail, which in this case r0 represents 0.5 of the total area, where z is just greater than 0 or equal to 0. And let's try r 1.25. Now this one represents the tail starting from 1.25 to positive infinity, or just z is greater than or equal to 1.25. And that's it. It's very easy to use the calculator to find the area compared to the z table. To wrap up the discussion, we're going to list what we've learned so far. We've learned that the area under the normal curve represents the probability in a continuous random variable probability distribution. Now the z table lists the areas under the normal curve, which we're going to use as a tool to find those. That the probability of z exactly equal to a constant is 0 for continuous random variables, and that the total area under the normal curve is equal to 1, much the same as the discrete probabilities, and that the areas can be added and subtracted together to get a certain probability or a certain region in the normal distribution. Thank you for listening.